Now, the next thing is called as wavelength. Now, what exactly is a wavelength in case of transfer wave?
It's the distance between two crests or two troughs.
Mm, there is one word which is missing. Think about that.
Parallel distance?
No, no, no. The distance between two consecutive crests
Okay.
or two consecutive crusts. Why consecutive? Because if you say two crusts, it can be that and that as well.
Yeah.
So this is not the wavelength. Wavelength is the distance between two consecutive crusts, one after another. Same thing for one trough, two consecutive troughs. So just write a definition. Distance between two consecutive crusts or two consecutive troughs is called as
Yeah.
wavelength, represented by this sign. We call this sign as lambda.
Yeah.
And what is a standard international unit for that?
Lambda? It's
Lambda,
meters.
yeah, meters. Lambda is just to denote the thing. So it's meters. There is another definition, you will find it in the books. That is very interesting definition. The distance between the 2 points on the wave which are in phase. Now, what is meant? First of all, write it down. The distance between 2 points on the wave which are in phase. Now, what does it mean actually? Phase means if you draw a straight line between the 2 points, they should meet like this, a straight horizontal line. This is in phase. This is in phase. But if I draw that line, this is not in phase. That is not in phase. In phase means a straight line when you touch those points, it will be a proper horizontal line. That is what we called as in phase points. But mostly the definition we have written, the first one, is the actual definition, that distance between two consecutive thrusts or two consecutive troughs. Okay?
Yeah. So when we see the 2 points, the two crests, they look like a wavelength, but then the other 2 points, they look smaller than a wavelength.
What do you mean the other two?
Like the P and P over here, the distance between them looks like a wavelength. But if
Okay.
we took any other distance, it
Like,
doesn't really look like a wavelength.
you mean these ones?
Yeah, this looks like a wavelength, but like,
You mean shorter than the previous one?
yeah,
It looked like, but actually in reality, it should be the same as the previous one. Because actually at the end of the day, it is drawn by the human, right? So that's the reason it looked
yeah,
like that a bit smaller. But remember that the distance should be same. It won't be different. Okay?
yeah,
It's not possible actually, because otherwise the theory will be wrong. Because it is constant everywhere. Yes, practically speaking, if you ask me practically, yes, lambda do changes because it's practically, so many things are there. But for the time being, we just started the wavelength, and here for the time being, you just remember that the whatever the wavelength of a wave, it will keep the same for all the wave which is going, which we study. Okay, it's not changing.
yeah.
All right. Now, once you understand the wave and everything, what is the example of the transfer waves?
Sound?
No, sound is not a transfer wave. Sound is basically a longitudinal wave. The best example for the transfer wave is light. Now, if
Yeah,
now you will ask me that light is EM, electromagnetic wave. So I didn't say that light is not EM, but problem is the shape of light is like this because these are the kind of waves having the shape. Transfer waves and longitudinal waves are differentiated on the basis of their shape, not on the basis of they are passing through medium or they are not passing through medium. Okay. So light actually travel in the
yeah,
form of these crust and troughs. Then we have water waves. We got waves in, I think these are the major waves we have it. Water waves, light waves, wave produced in a rope. Next topic will be we having a standing wave, like you will band, I mean, attach the rubber from two sides somewhere, and then you start, plucking it. you will find the wave. These are the same kind of transfer waves. Okay. So this is the
Yeah.
type of transfer wave.
Yes.
Now put a heading longitudinal wave. Let me just come to that. Now, what is longitudinal wave, first of all? Interesting fact is in longitudinal wave, if you see the particles, particle somewhere are compressed, somewhere they are a bit far away from each other, then they are compressed, then they are far away, then they are compressed, then they are far away. Let's take an analogous example which make you understand what is that kind of thing. Do you ever see a spring? Definitely you seen it, don't you?
Yeah.
My question is, when you expand that, I mean, when you stretch it as a bodybuilder or as an exerciser, and you left it after some distance covered, what is happening? Does it just close and finished?
No.
Then what happened?
It compresses some places.
So basically, when you compress, I mean, when you left it, it will go like this. It will compressed. One position, it is compressed, and then after compression, there will be a restoring force that try to restore your spring back to its original shape. So it will elongate. Once it will elongate, again the restoring force try to restore the original shape. And for doing this, it will again compress.
Yeah.
And this will happen until it achieves a equilibrium condition. This is your equilibrium condition, the actual condition where there was no wave. But before that, it will extend, compress, extend, compress, extend. So did you see that it's not actually leaving at one point, but it will continuously just compress and expand, compress and expand, compress and expand. So these are the actually example of a longitudinal wave. Same thing happen in the longitudinal wave that when the particle is moving, somewhere the particle of the medium are compressed. So you can say they are compressed and somewhere the particle of the medium are expanded. I mean, you can say far away from each other. Then compressed, then far away, then compressed and far away. So this is what we called as longitudinal wave. So how to explain that? The particle are compressed and expanded in the same direction the wave is traveling. Am I right?
Yeah.
So how do we explain that? How do we explain the longitudinal wave? That in longitudinal wave, the motion of the particles of the medium is parallel to the direction of the propagation of wave. And both
Yeah.
have the same direction. Or you can say the angle between the direction of the propagation wave and the particle motion is 0 degrees. So that
Yeah.
type of motion or that type of disturbance is called as longitudinal. All right. So I want you to put a heading longitudinal waves and write a line. I mean, write a definition. Longitudinal wave is the oscillation. Longitudinal wave is the oscillation in which particle of the medium travels parallel to the direction of the propagation, in which particle of the medium travel parallel to the direction of propagation of the wave.
Yeah.
Okay. I want you to draw this diagram quickly. Let's suppose you got one engine and behind that you got one, two, three, four bogies, or you can say one compartments. My question is, when it is going, and suddenly it stops here, what will happen? This bogie hits that bogie here, This boogie hits that
Yeah.
boogie here, and this boogie hits that boogie here. Then what happens? When it hits, it go further. So that
Yeah.
side will be far, and this side will be behind, and this side will be behind, and this side will be behind. Then it hits, and
Yeah.
then this condition comes. Then it hits, then it expands. So it will keep working, it will keep going like this till the engine actually stops. So this is again an example of a longitudinal wave. Wherever the particle are in the oscillation, remember that that particular things or that particular waves are longitudinal waves. Do you ever see do you ever see a pendulum?
Yeah. A pendulum.
Pendulum, and you know that pendulum is sometimes used to hypnotize people as well, by simply
Yeah.
hanging it. This is also a long example of a longitudinal wave, by the way, because here it's a vibration, but we normally don't give that as a vibration because this is something to do with the harmonics and everything, which I think is your second part. Not in this year you will study. Next year I think you will study that harmonics and all this.
We do have harmonics. We have simple harmonic motion.
Do you have it in the same waves or not? No, not in that.
Yeah, we do.
Is
We
it
have. Simple, yeah.
in the
We did a
wave?
practical first.
No, no, I
We
know.
had.
But is it in the wave or not?
I think it is. Yeah, because we do like when we do questions, we use simple harmonic motion.
Okay, okay, okay. If it's there, then. But as far as my knowledge is concerned, this is not in that unit we are studying. It was something related to some other unit, might be. Anyway, you will check it out and let me know. Because as far as my knowledge is concerned, this might be in unit 3 or unit 4. Okay, but let me know. No problem. If it's there,
Okay.
we will do that. Okay, one more thing. Is capacitor or the capacitor circuits are in our course? You know that.
Capacitor.
Do you ever heard of capacitor, by the way, first of all?
I've heard of it, but I don't think we've used it.
Then it's fine. Because actually, it's also there in your course, but I am confused that is it in electricity or not, because it's a part of electricity, but I never see in our unit for a very long period of time. So I asked you because the syllabus changed, just by some
Yeah.
source or something, confirm it if the capacitor is a part of electricity or not. If it's not, then maybe you will study them next year. When inshallah you come back next year, I mean in the next units, then might be your capacitor we will study over there. So just I want you to confirm it two things. One, capacitor, and one your harmonic motion. Is it a part of this year anyway, somewhere, unit 2 or unit 1? Okay. So you need to ask these two
Okay.
questions. Okay, now
Yeah.
here, so when will you tell me that? Tomorrow or day after tomorrow?
I can send you my specification. This the one that I have is the latest one.
Okay, then send it to me, okay, by WhatsApp or something, no issues. Okay, now we are
Yeah.
here, right? Now the important
Yeah.
thing is, did you write that? Did you draw that?
Yeah.
Okay, now the same thing happens if you check this out. Here particles are very nearby here. Here the particles are far away. Again, nearby, far away, nearby, far away. So what we say, like previously we had crust and trough. Here we have particles are compressed, so we called it compression. And where they are a bit far away, we called it rarefaction. So
Okay.
basically, when particles are compressed or close by, we called it the particles are in compression. When they are far away, we called it rarefaction. So in a one bullet line, I want you to write the compression and then write one line of this. It is a part of a wave. It is a part of a wave
Yeah.
in which particles of the medium, in which particle of the medium are close to each other, are close to each other.
Okay.
And then again in the next line, put a heading rarefaction. In this region, particle of the medium, in this region, particle of the medium far away from each other.
Yeah.
Okay. In this case, what will be the definition of the time period technically? So put a heading time period. Now, what is time period in this case?
Uh, The
We,
time taken to
yes, time.
pass the wave.
Now here actually mostly we don't use wave. Instead of that, we called it vibration. It's a sort of a vibration. We do call it oscillation, but we do call it wave as well. But particularly, these are called of vibration because they are to and fro motion. So vibration or oscillation are the best word we can use here, especially. So you can say in time to complete one complete vibration or oscillation is called as time period.
Yeah,
Okay. The second thing is frequency. Same thing. Number of vibrations or oscillation passing in 1 second is called as frequency. Same
yeah.
formula, each and everything will be same. What is wavelength in that case?
The distance between two consecutive compression and rarefaction.
Yes, that is it. Also write that as well.
Yeah,
Now the last but not the least one is displacement. Distance from the that one was a particle distance from the mean position. Here, what is the mean position? Somewhere in
um,
the middle, actually. So the distance
yeah,
from the mean position is basically the particle. Let's suppose if you are finding the distance, the mean position is this actually. You have to consider every part is basically a mean position in that. It's not this one which is a mean position in that case because the particle of the medium are parallel. So basically, if you are asking for the distance, then basically distance from one crust to another crust is technically you're talking about the displacement or amplitude. If you are asking about the maximum one, then it will be maximum. Otherwise, it will be minimum. But normally, they don't actually ask you in this case what is uh, what do you call it, displacement or amplitude, because here amplitude is related to the mean position. While here, what is the mean position? That is a bit difficult to ask, a bit difficult to think of. But remember that here, wherever you think is a mean position, the distance of your call it your particle from that point, especially this point is there. So if you are finding the sort of a displacement, then this is your displacement, this is your displacement, this is your displacement. But maximum displacement is from this point to this point. So this is your amplitude, or the small displacements are your small displacements. Understood?
yes, sir. Can you give me 2 minutes? I'll come back.
Please, please. So So they are almost the same. Now, let's quickly end up our lecture by simply differentiating these two waves. So put a column transfer wave at one side and on the other side, longitudinal wave. Let's quickly see the differences between the transverse and the longitudinal wave. What is the first
Yeah.
difference? Their definition. So, Manur, what is the definition of a transfer wave?
The particles are perpendicular to they travel perpendicularly to the direction of the propagation of the wave.
Yes. And what about in longitudinal?
Particles travel parallel to the direction of propagation of wave.
Please write it down quickly so that you will keep a record of each and everything because this is very important. What is the second point which can be a contrast between these two?
Um,
Example,
Transverse have crest
example.
and troughs.
Yeah. So crust and troughs are formed in transfer waves, while in longitudinal waves, compressions
Compressions and rarefactions.
are formed. And the third can be the example. So what is the example
Yeah.
of transfer waves?
Water waves.
Light waves.
Yeah.
And what about the longitudinal waves?
Sound.
Sound waves, right? Okay. I think these are enough. Now let's move to the related topic, but a bit different topic. Let's see. This is called polarization. Now, what is this word polarization? That is very interesting, actually. Polarization mostly used when you're talking about EM waves. Remember that. You know, do you ever see an antenna sort of a thing or dish LNBs in your place, in your somewhere on the top?
Yeah.
So that is a purpose of actually using this polarization. Now, what exactly is polarization? Actually, polarization restricts the oscillation of wave to one plane. Now, what is meant by to do in one plane is because actually we want that our satellite will actually get the maximum number of wave from satellite, because in that way our what you can say, we if the antenna gets the maximum number of waves, the communication will be as good as possible, and definitely the channels whatever you have it will be a better, like your reception will be as good as possible. So that is why polarization restricts the oscillation of a wave to one plane, because if it will be in multiple planes, it will be dispersion, or you can say it will be scattered all over. And if it will be scattered all over, the communication will not be considered as very good, what you call it, very good communication. So that's the reason it restricts the communication in one place, or you can say it will just restrict the oscillation to move or whatever they want to do in one plane, either x plane, xy plane, or yz plane, or xz plane. In the diagram, the light is initially oscillating in all directions. A piece of Polaroid only allows light to oscillate in the same direction as it is. In the top diagram, the light passes through a vertical plane, polarized, Polaroid, and become polarized in the vertical plane. This can then pass through the second vertical Polaroid. In the middle diagram, the light become polarized in the horizontal plane. So what exactly it is? These are basically the sort of equipment which you normally see in your antenna. You know, these, if you see your antenna, I don't know, do you ever see the antenna? It's like a sort of a long stick. Along with that, you will have that these kind of, these kind of things. Do you ever have any chance to see that?
Yeah, I have.
So actually, these are the things which actually these are called Polaroid, and their function is to actually uh, polarize your signal in one plane depending upon how they want it to be. Sometime it will be in vertical and sometime it will be in horizontal. So before it, if you see that there, they are in a multiple directions. But as soon as it is passing through this Polaroid, actually, then it will be in one plane only, either vertical plane or either horizontal plane. All right. So I want you to write this quickly, full from top to end, polarization. This is important actually. Just take a quick, you can say, intro of what we inshallah will continue tomorrow. Our tomorrow topic will be basically total internal reflection. This is very much important. Do you
Yeah.
ever have an idea? Do you ever study this total internal reflection?
Yes, the GCSE.
So basically, total internal reflection is everything to do with the light, technically. But what is the application? That's what we will see in the details. I just give you an idea. Is there any difference between total internal reflection and general reflection?
Total internal reflection is when the reflected ray is, well, it's doesn't refract, it stays in the medium.
Actually, is there any difference between a general reflection and total internal reflection, by the way?
Yes, the critical angle,
Critical angle and what else?
the density of the medium.
Actually, we will see in details actually. When it's total internal reflection especially occur, or you can say a special condition for that, when light goes from denser to rarer medium. Only and only
Yeah.
this will occur when light goes from denser to rarer medium. Otherwise, there nothing like total internal reflection. We will see to it in detail what is denser medium, what is rarer medium. I will give you special notes on that. So that is the first
Yeah.
condition. And second condition is, as you just said it, the critical angle. The incident angle or angle of incidence must be greater than the critical angle. If this will not be the situation, total internal reflection may not be occur. Okay. And then there is another very important condition. When we study reflection, it doesn't mean there is no refraction. So it means that reflection and refraction occur at the same time, but definitely because we are studying reflection, so we are not focusing on refraction. Because, for example, if there is a window in your room, what do you think? It only reflects, or it will not refract a single light beam? Is that be possible? No, it's not possible. It means that might be, if I'm telling you in a sort of a percentage, might be 2 or 3% of the light rays actually going out of the medium. So it means that 97% of the medium, I mean 97% of the light waves are reflecting back into the same medium. So technically speaking, while a process or while this activity, reflection and refraction occur at the same time. Am I right?
Yeah.
But in total internal reflection, there will only be reflection and there will no more refraction. Totally reflection. So all the light actually comes into the same medium, right? So this is actually happening in the
Yes.
total internal reflection. Inshallah, we will be continuing this tomorrow. Okay. So
Yeah.
inshallah, see you tomorrow, same time, inshallah. Take care. Bye.